All right, we are at section 33.2, Maxwell's equations, and this this is what we're looking at. Just for reference, let me stop this share and see if I can find the images. Where's the? There it is. This, if you go on in physics, especially in electricity and magnetism, this is what your Maxwell's equations are going to look like. They're going to have the del operator in front of them. Gauss's law for magnetism, Faraday's law, and Ampere, Maxwell law. When you get later in your studies, I don't want you to say, oh, well, Mr. Menchaca didn't teach us these. I did. They're just in a different form in your book. They're the integral form. These are the del operator form, and the del operator is simply a differential equation form where you have you're differentiating in the three different axes. So let's go back to the what we're going to study. They're the same thing. So first we have Gauss's law. The integral of E dot dA is equal to Q divided by epsilon 0, the permittivity of free space. If you have the electric field around any surface area is the charge is related to the charge inside that surface area. So you can have an isolated charge inside a surface, and if it's a positive charge, a positive ion, you get electric fields coming out of it. If it's an electron inside the surface, you have electric field lines going towards it. And so the Gauss's law says that when you take a surface and you put a charge in it, the integral of E dot dA is the Q divided by epsilon 0. Now, integral of B dot dA, the integral of the magnetic field over a surface area is equal to 0. What does that mean? That means that for every magnetic field line that is exiting the surface, that means that there was a magnetic field line entering the surface at the same time. So that the sum, excuse me, the sum is equal to 0. What is that saying? That's saying, whereas we could isolate a positive charge or a negative charge and put it inside a surface and get an electric field, when it comes to magnetic fields, you cannot isolate a north pole or a south pole. There are no magnetic monopoles. In other words, they're always going to come in pairs, the north and the south pole. And so when the magnetic field lines make a loop, if one enters a surface, one is going to exit the surface. The total is 0, and that's Gauss's law in magnetism. Now, Faraday's law, integral of E dot ds is equal to the minus d phi dt of the magnetic field. What does that mean? That means that you get an electric field when you have a changing magnetic field. Remember, we talk about dB dt, dA dt, or d cosine theta dt. You can change the magnetic field by changing the magnetism, by changing the area, or by changing the cosine theta, the angle between the magnetic field lines and the surface. So without any of those changing, if phi, the magnetic flux is not changing, you have no electric field. It's only in the changing, excuse me, changing magnetic field that you get an electric field. Excuse me. Okay, then we just studied in the previous section the Ampere's Maxwell law. B dot ds is equal to the mu 0 times the current plus E0 mu 0 times the d phi dt of electric flux, the change in electric flux. So you can either have a magnetic field from a current in a wire or from a changing electric field. Now, let me go through my notes, make sure. These are Maxwell's equations hold in the absence of any dielectric or magnetic material. So Gauss's law relates electric field to a charge distribution that creates it. Gauss's law of magnetism says that magnetic field lines cannot begin or end at any point. Faraday's law of induction describes the creation of electric field by changing magnetic flux, d phi dt. Maxwell's law describes creation of a magnetic field by changing electric field and electric current. These are Maxwell's laws, and we're going to look at Lorentz's force law. The combination of Lorentz's force law and the Maxwell's equation is completely describe all classical electromagnetic interactions in a vacuum. So the Lorentz's force law says that a force acting on a particle of charge Q can be calculated from the electric and magnetic versions of particle in a field model. So the force is equal to either QE, the charge on the electric, cause a charge in an electric field experiences the force, and the charge times a velocity, velocity cross B, you get a force also. You remember the right-hand rule. You have a magnetic field, you have the velocity, you have a charge. If it's positive, it's at the palm. If it's negative, it's at the back of the hand for a moving charge. And then we throw in the Maxwell's equations on top of that. Now, the result led Maxwell to predict that light waves are a form of electromagnetic radiation. Let's see. I should say a little bit more about. Note the symmetry of these. Integral of E dot dA equals 0. Integral of B dot dA equals 0, and that this occurs as a which when in the if you imagine a region of space that contains no charges and no currents, so there's no Q and there's no current, there's no I, then Maxwell equations reduce to this, and there's some symmetry here. The integral of E dot dA equals 0. Then if there's no charge, then there is no electric field. The integral of B dot dA equals 0. The magnetic field lines are in loops, and the line integrals E and B around a closed path relate to the change in magnetic flux and electric flux respectively. The equation suggests that electric and magnetic fields can exist in charge-free, current-free space. They regenerate. Excuse me. They regenerate each other. The time variation in the B field generates the E field. Okay. So let's go on. Hertz's experiment verified this. He had a transmitter consisted of two spherical electrodes connected to an induction coil, which provides short voltage surges to spheres, setting up oscillations in the discharge between the electrodes. Excuse me. And the receiver is a nearby loop of wire containing a second spark gap. Now, the discharge between the electrodes exhibits oscillatory behavior at very high frequency. And the experimental apparatus was equivalent to an LC circuit, and the inductance was that of the coil, and the capacitance was due to the separation of the spherical electrodes. Now, L and C were small in Hertz's apparatus, which means the frequency of the oscillation was very high, on the order of 100 megahertz. And recall that omega is equal to 1 over the square root of LC for an LC circuit. Now, the receiver loop, placed several meters from the transmitter, has its own effective inductance, capacitance, and natural frequency of oscillation. So his experiments was evidence that radio frequency waves were generated and that had properties similar to those of light waves. They differed only in frequency and wavelength. Waves of known frequency reflected off of a metal sheet and created standing wave patterns. He measured the distance between nodal points from these reflections and determined the wavelength lambda using the relationship V equals lambda F, where F is the frequency, lambda is the wavelength, and V is the velocity. And he came very close to the velocity is equal to 3 times 10 to the 8 meters, which is the known speed of visible light. Okay, and let's stop there, and we'll continue on with 33.3 in the next mini lecture.